All right, so now let's talk about the oxidation of alcohols. Okay, so we learned a bunch of techniques for synthesizing alcohols by reducing ketones or aldehydes or even esters and carboxylic acids, but we can go the other direction as well by oxidizing alcohols and forming ketones, carboxylic acids, aldehydes. Okay, so that would be going the other direction where you're creating more carbon-oxygen bonds. Okay, so if we have a primary alcohol, we can oxidize it one step to form an aldehyde, and then we can also go one step further and oxidize our aldehyde and form a carboxylic acid. Okay, so that would be two sort of oxidation steps. We'll see that a weak oxidizer can stop at that aldehyde step, but a strong oxidizer will go all the way to a carboxylic acid. There's no way to halt a strong oxidizer at that aldehyde step. When you're talking about secondary alcohols, you can only go to a ketone, whether you use a strong oxidizer or a weak oxidizer. You can only sort of perform as many rounds of oxidation as you have hydrogens. So in this case of a secondary alcohol, you can only have one round of oxidation. There's no sort of further step. And by that same logic is if you have a tertiary alcohol, there's no oxidation reactions that are possible. Okay, so you can't oxidize tertiary alcohols. All right, so we're going to first learn about our strong reducing agents, and these all have one thing in common, which is the chromium atom. Okay, so whenever you see chromium in a reaction, you should be thinking strong oxidizer. The most common ways that you're going to see that is with this sodium dichromate, along in the presence of H2SO4 and water. Both of these are, whether you start with the chromium trioxide or sodium dichromate, both of them actually first form chromic acid. Okay, so chromic acid is the real player here. You'll often see this abbreviated H2CrO4. All right, so this is what you want to sort of spy. In my experience, being able to spot this and being able to spot this is really important. I've honestly never seen this before. But again, if you get surprised on an ACS exam, whenever you see chromium, you're thinking strong oxidizer. Okay. So what does this mean? Well, so again, chromium is a strong oxidizer, so it will take an alcohol all the way to a primary alcohol, all the way to a carboxylic acid. You cannot stop at this aldehyde step when you're using a chromium-based oxidizer, okay, or chromic acid. If you want to stop at the aldehyde step, you have to use a weaker oxidizer, which would be, and we're going to see a few examples of this. By far the most common that you see all the time is PCC. PCC actually does involve a chromium as well, but it's like a special designer kind of thing, and you will always see it abbreviated PCC. And in this case, the CaH2Cl2, that's indicating that it's taking place in a dichloromethane solvent. Okay, but notice here we can get PCC is considered a weak oxidizer. So this is what would happen if we used that chromic acid. If we wanted to stop at the aldehyde step, then we would use PCC, right? PCC can oxidize alcohols to aldehydes, but it can't further oxidize an aldehyde. So it turns out that, okay, so before we move on, in the case of a secondary alcohol, both strong and weak will do the same thing, right? So here was our example of a strong oxidizer. This is the other one with the sodium dichromate. Again, it's all about training for the ACS exam. I know that it would be wonderful if I just gave you guys one oxidation technique and we've stuck with it, but it's all about being able to make sure that you can spot what's going to go on the ACS exam. And again, the sodium dichromate, along with the sulfuric acid in the water, is another thing that you want to spot and be able to say, that's a strong oxidizer. The PCC is a weak oxidizer, but if you're starting out with a secondary alcohol, both of those will take you to a ketone. There's no way that you can oxidize beyond a ketone. All right, so now we're going to learn about two other weak oxidation techniques. So basically those chromium ones, they work great. Chromium is insanely toxic, whatever form you use it in, chromic acid, anything like that. And terrible for the environment, which means that if you're a chemist trying to use it in your lab, number one, you have all these health concerns to worry about. Number two, disposing of it properly is really, really expensive. So there have been other oxidation techniques that have been formed over the years that don't require these chromium based. And so we want to be able to spot those too. So the first one is called a swern, and the key player here, swern's obviously the guy who invented it. The key player here is this molecule here. And so what does this look like? It's kind of a weird way to write a molecular formula, but that refers to this compound here. This is the key player, okay? And again, it's all about being able to spot things on the ACS exam. So this is our other weak oxidizer that we're going to learn about. We don't even really have to know the mechanism. All we need to know is that these weak oxidizers will convert primary alcohols into aldehydes and secondary alcohols into ketones, but they won't further oxidize an aldehyde to carboxylic acid. Right, so this is swern oxidation, and again, that key player is the COCl in parentheses 2. The other one is this Des-Martin Pyrodane oxidation, importantly, or rather abbreviated DMP. And so DMP refers to this kind of cool designer molecule here, but again, what we really want to be able to spot is DMP and dichloromethane. That will again serve to be a weak oxidizer. And will oxidize a primary alcohol to an aldehyde, but won't further oxidize to a carboxylic acid. And just like all of our other weak oxidizers, it can get a secondary alcohol to a ketone. Okay, but so DMP is our third weak oxidizer that we're going to learn about. Okay, so here are our two strong oxidizers, the patterns that I want you to know. Again, the book had this here. I'm not going to worry about that one. In acetone and acid or something like that. I've never seen that one before, so we're not going to worry about it. But should you come up on the ACS exam and see these things, what you want to remember is chromium means strong oxidizer. And so both of these these are our strong oxidizers. So let's take a look at what they'll do to this molecule here. Here in this molecule, we have a secondary alcohol, we have a primary alcohol, and we have an aldehyde. Well, remember, our strong oxidizers will oxidize primary alcohols all the way to carboxylic acids. They won't stop at that aldehyde step, which means that they'll also oxidize aldehydes to carboxylic acids. And then the secondary alcohols always get oxidized to ketones. So if we look at this product here, our primary alcohol will be converted to a carboxylic acid. Our aldehyde will be converted to a carboxylic acid, and our secondary alcohol converted to a ketone, again, because these are our strong oxidizers. So then we learned about three weak oxidizers. What's the whole shtick with the weak oxidizer? It stops at that aldehyde step. So we have the same molecule here, a secondary, a primary, and an aldehyde. One, two, three, four, five. 1, 2, 3, 4. Our weak oxidizers, they can't react with aldehydes, so that's just going to stay an aldehyde. They will they will oxidize a primary alcohol just to an aldehyde and stop there. And then a secondary a secondary alcohol will always be oxidized to a ketone. Right, so instead of getting these carboxylic acid groups, our weak oxidizers will stop at that aldehyde step. So notice that this is the same. What happens to our secondary alcohol, always the same. The difference is what happens to aldehydes and our primary alcohols with weak oxidizers that will stop at the aldehyde step.